We're going to continue our discussion of solving triangles by looking at some applications. Specifically, the first one we're going to look at are vectors. And we're going to look at geometrically defined vectors, and then we'll look at how to define them algebraically. Algebraic definition and geometric definition are different, and we'll kind of explore that as we go. A vector is defined as having two main traits. One is its direction, and the other is its magnitude or its length. Okay, so vectors have a direction and magnitude. Okay, so there's two important aspects to a vector, all right? Now, you could draw a vector. That's the geometrically defined vectors, kind of how we draw them, how we represent them visually. The algebraic one is how we represent them mathematically with numbers and letters and stuff like that. We will talk a little bit about variables and stuff here and how to represent them, but generally speaking, this is more of the geometric part, the picture aspect, okay, or the shape aspect. So a vector will have two different things. Its direction, which can be defined a couple different ways, but for right now I'm going to call it an angle. So maybe you think of it as kind of an angle theta. And its magnitude. The magnitude is the length of this vector. And we'll call that, now if this is, let's say this is vector v, we'll call this the absolute value of v, or the magnitude. Absolute value symbol is the symbol that we use for a magnitude. Now, a vector can have, we usually use a couple different types of variables for vectors. We can use either a bold-faced letter, like vector v has a bold v, or you could write it with a little, we call them harpoons or arrows. It's not a full arrow because an arrow would have both angles on top or on the right side there, but I call this a harpoon because it only has one side. And so vectors, when you see them written in a textbook or on a test, they could either be written in boldface or with a little harpoon over top. Because it's hard for me to distinguish when I'm writing up here a bold versus a regular letter, I'm going to use the harpoon over top, this one here. So when I write vector, this is vector v, then the magnitude, I'd use that little harpoon in there as well for the magnitude, okay? So vector v, these are variables to represent a vector. Okay, and you'll see, mostly in your textbook, you'll see the bold-faced one right there. On my math lab, you might see a combination of the two. When I'm writing at the board here, I will tend to use the harpoon. And actually, when I write tests, I also tend to use the harpoon, just to be consistent. But just note that you could see either of those notations to represent a vector, okay? And it's just easier to use, there's some sort of way to distinguish a variable for a vector than for, a variable like a scalar quantity, like the variable x or y in an equation. So obviously the letter v is different than what we normally would use, but sometimes we might use the letter v to represent a regular scalar variable rather than a vector variable. So we want to distinguish the vectors from the scalar variables anyway. So we'll use one of these two notations. Okay, so that gives us just a basic definition. You can move vectors around and they don't change. So the same vector could be in one location and in another location. That is not the same direction. They just have to be pointing in the same direction with the same length. All right, so both of these vectors, assuming the same length and the same direction or angle, are going to be called vector v. All right, or they're the same thing, same vector. All right, so vectors do not have a specific position. They can be moved and not changed. Okay, so vectors do not have a specific position. Okay, so they can be moved, they can be found in different locations, and still the same thing. As long as they have the same direction and the same magnitude. Okay, that's what they need to have. Okay, so a direction, I mentioned this a moment ago, but I'll re-emphasize it. A direction is basically an angle, and the magnitude is basically a length. Okay. Now you're going to have 2 points on a vector. There's going to be something called an initial point and a terminal point. Okay. The initial point is kind of where it starts, and the terminal point is where it ends. The direction from the initial point to the terminal point is the direction or the angle of the vector. Okay, so we have, let me write those up in another color. This would be the initial point. And the terminal point. Okay? So the terminal point is at the end in the direction that it's pointing toward. Okay. Now you can have, you can change the size of a vector. If I wanted a vector that is twice the size of vector v, 2v, then you want a vector that is, this would then be a new vector, and it is basically a vector in the same direction but now twice as long. So instead of just v by itself, I might use 2v. Let's see if I can get that roughly accurate. Let's bring that out just a smidge further. Okay, so let's say that one is 2v. It's roughly the same angle. Well, it needs to be exactly the same angle, but it's roughly based on my picture. It's exactly the same angle and exactly twice as long, and that would be vector 2v. Okay. Now 2v is the same as v plus v, right? So you could think of them. You think of those as the same, right? 2 of the same vector, 2 times a vector, or a vector plus itself. Same thing. And so you really have, sort of halfway here, you have 2 copies of vector v. Here's v, and together they make 2v or v plus v. Now, if you had 2 different vectors, we'll call them vector v and vector u, for instance. Or maybe we'll go v and w. I'm going to save u for something else. So let's say you had 2 different vectors. We'll say vector v, and it goes up to the right like this. And let's say we have vector u, a little bit shorter, going down to the right. Okay? No, I didn't want to use u, I want to use w. Sorry. Vector v and vector w, there you go. Now, I can add those vectors together geometrically by just linking one of them to the end of the other, okay? And then finding the resulting vector. So if you consider this is v, and if I link vector u, or vector w, I keep saying u, to the end of vector v, then the resulting vector is one that starts at the initial point of v and ends at the terminal point of w. It would be this vector here, the dashed one. And that dashed vector would be v plus w, okay? Now, vector v plus w is a new vector with a new angle and a new length, okay, or magnitude. So it has its own magnitude, it has its own angle. And it is basically the third side of a triangle whose other sides are V and W, all right? So V plus W is the third side of a triangle with V and W as the other sides. Okay, so pretty simple there. Some people would also consider it a diagonal to a parallelogram. Okay, and this is going to be an important aspect as well. If you were to draw out or finish out a parallelogram containing vectors v and w, let's assume that's all parallel there, which is not perfect, but it's close enough. Okay, so this is vector w again, this is vector v again. Then you could say that v plus w is one of the diagonals in the parallelogram formed with v and w as the two main sides. Okay. Now the other diagonal is kind of important. What you get with the other diagonal, let's see. Let's plop it in. Well, maybe I'll redraw that just so you can see it separate from everything else. So there's V. That's a little big for V, I think. All right. Obviously, I'm really rough sketching these in. Okay, so there's my parallelogram, right? Parallelograms, some features of parallelograms that are very important is that opposite sides are the same length, okay? Opposite angles are the same, they're congruent. And also the diagonals of a parallelogram bisect each other, but they don't necessarily bisect the angles that they go through, okay? So this diagonal here bisects the other diagonal, so they meet right in the center, but they don't necessarily bisect the angles. The angles that are created by a diagonal are not always the same. Okay, so if I draw in the other diagonal here, here's V, here's W. How would you represent that using a vector? Well, what's interesting is if you consider going from the bottom to the top here, what you're doing is you're going backward along W and then up along V, which is negative W plus V, right? So you could think of that as negative W plus V. So because you're going backwards up W and then up along V. Well, if you interchange those two terms, you would also get equivalently V minus W, right? Negative W plus V or V minus W, the same thing. So we'd say the other diagonal is the difference between V and W, okay? So one diagonal is V plus W, the other diagonal is V minus W, all right? Okay, and of course they bisect each other, which means they intersect right at their midpoints, if you consider them as segments. Okay, so there's just a couple pieces of information, a couple interesting facts about vectors. And of course you can then add and subtract any number of multiples of these vectors together. Once you've established a few set vectors, you could add 3v minus 2w, and then you just have to link them all together, right? You link 3 v's together and then go minus 2, so you do w in a negative direction, the opposite direction, and that would give you the corresponding vector for that. Okay, so I'm not going to draw it all out and run out of space, but kind of get the idea, hopefully, is that you're just taking 3 vector v's, 1, 2, 3, 2 w's in the opposite direction, and then you would link them end to end, and that would be your new vector. Okay. Okay, so we can also multiply by other scalars or numbers. A scalar is just a number, it's like a real number. But you could do something like 1/3 of w, right? 1/3 of w is simply the same direction or angle as w, but only taking 1/3 of its length. So it might be something like that, right? It's 1/3 the length of w, but in the same direction as w. So you can expand these out, you can shrink them down, and so forth. There is something called a zero vector. The zero vector is one that has 0 length. I often will represent it with a 0 with a little harpoon over it. It has 0 length, and it doesn't have a specific direction either, because how can you point a direction if you're just basically a dot, right? Some people would say it has any direction you need it to have for a given problem or a given scenario. I would say it doesn't have a specified direction. So the zero vector, I'll write that up here. The zero vector has 0 magnitude and no specified direction. Okay? So that's the zero vector. Okay, so that gives you kind of an overview of some of the things we can do geometrically with vectors.